Hello everyone, welcome to our differential equation class. In this video we are going to introduce a new type of differential equations called second order linear differential equations. We are going to start with the main definitions and then what is the main example of this type of equations, Newton's second law of motion. Then we are going to go deeper into these equations, in particular cases of this equation, and we are going to uncover something that is called the conservation of the mechanical energy. So that's the plan for today. Before we start, let's review what is a first order linear differential equation. First order linear differential equation is an equation of this form where we have the first derivative equal some function of time times the unknown function plus another function of time. The equation is linear, we said, because the unknown functions on the right hand side appear with power 1 or with power 0. So that was a first order, and it's first order because the maximum derivative is the first derivative. We can rewrite this equation, of course, putting all the y dependence on the left side, and if we do that we get this expression here. And we also said that this equation has constant coefficients if both the coefficient a and the coefficient b both are constant. So now what we are going to do is we are going to introduce second order linear differential equations, and the second order is because the second derivative of the unknown function is going to appear in the equation, and then we are going to have all the other derivatives, the first derivative and the zero derivative. And we are going to write these equations in this way: the y dependence on the left side and the rest on the right hand side. These equations were first solved by Leonhard Euler around 1739. He showed how to solve these second order linear differential equations first without homogeneous, that is without this term, so 0, and then the non-homogeneous with constant coefficients. And constant coefficients, when we talk about constant coefficient in this equation, is going to be different from constant coefficient in first order equations. In second order equation, constant coefficient is going to be only this coefficient constant, and we are going to leave the right hand side arbitrary, which is different from the convention we had in first order. So heads up about that. Okay, so we are ready for then all these main definitions. So what are the main definitions? Well, what we said before, a second order linear differential equation is an equation then of this form where the unknown function appears with second derivatives in the equation, may appear with first derivatives or not. This coefficient could be 0, and the original function could appear in the equation or not, depending whether this coefficient is 0 or not. In general, it's going to be an equation of this form, and the right hand side contains all the terms without y dependence, and it's called linear because the dependence in y is always with power 1 on the left hand side. We say that we are going to call the equation homogeneous when the right hand side is 0. We said we are going to call this equation that has constant coefficients if a1 and a0, only these coefficients are constant. We don't say anything about b, and it's going to have variable coefficients with either of these coefficients, a1 of a0 is not constant. Maybe the main example of a second order differential equation is Newton's equation mass times acceleration equal force that describes the movement of a point particle in one space dimension. To see that actually this equation is a second order differential equation, let's introduce the the function y of t, which is going to be the position of the particle as function of time. We need only one function because we are moving in one space dimension. We call that dimension y. Then the derivative with respect to time of that function is going to be v of t, the velocity of the particle. One more derivative, so the second derivative of the position function with respect to time is one derivative of the velocity. This is what we call the acceleration of the particle. So we can replace mass times acceleration equal force by a more precise way of writing that equation, which is this: mass times the second derivative of this is the mass of the particle that we are studying. Then the second derivative of the position function is equal some function of time. The function can change in time. The function can change also in position in space, and the function also can change depending on what is the velocity of the particle. As we see here, this is a second order differential equation, and this equation is going to be linear depending whether the force is linear in the position and in the velocity. For example, suppose we have a force function that has this expression, some function of only time, and then coefficient times the position, coefficient times the velocity. So this is a linear function, linear function of position and velocity. So in that case, what happens with our equation mass acceleration equal force? Well, we have mass, second derivative of the position with respect to time, equal this force, which is v tilde, could be a function of time, minus a coefficient here, the position, minus another coefficient that can depend on time, times the velocity. So we can write these two terms on the other side, of course. And if we do that, we end up with a mass acceleration plus, let's say, a1 times the velocity plus the coefficient a0 times the displacement or the position of the object is equal the term v of t. So as we see here, this is a second order differential equation and it's linear, but we have here a coefficient in front of the second derivative. So if we want to have the expression exactly the same as this expression here, the only thing we need to do is divide by the mass. And then we have here y double prime plus some coefficient a1 of t, but now we are going to divide by the mass of the particle, y prime, plus a0, we divide by the mass, y, and here b of tilde of t, and we divide by the mass. So this is exactly the equation we had before, where all this coefficient is what before we called a1 of t. That's why the different names. This coefficient here is a0 of t, what we called before, and this is the coefficient b of t. With those definitions, the equation we are writing is acceleration equal force divided by mass. That is a second order linear differential equation. So, as a summary, we can say notice that this is the most general expression of what we called before a second order linear differential equation, and these are equations of this form where this equation describes particles, point particles moving in one space dimension. Therefore, any second order linear differential equation can always be associated with a point particle moving in one space dimension under a force that is linear in displacement and speed. That means we have a lot of physical intuition that we can use to get the solutions of this equation, because these equations have to describe point particles moving under Newton's equation of motion. But, as we said before, in one space dimension. our world is three-dimensional. So what happened in that case? Can three-dimensional system be described by this equation? Because this is only for one-dimensional systems. So the answer is yes, and is our next example. Our next example is a mass spring system which is three-dimensional. So it's a perfectly three-dimensional system. What happens with this three-dimensional system is that it's moving in one space dimension. So here we have a little picture of the system. We have, for example, a spring hanging from the roof, and we attach to the spring a mass, an object with mass m. Then the spring is going to stretch a little bit, and it's going to reach a position of equilibrium, so it's going to stay at rest after a little while. And what happens here is that because the object is at rest, Newton's equation of motions they are telling us that the mass times the acceleration of this object, because it's at rest, there cannot be any forces, so this has to be 0. However, we have two forces. The weight, which is proportional to the mass of the object, and the acceleration of gravity on the surface of the Earth, which is 9.81 meters over second squared. And we always have this weight, and then there should be a second force, which is the force that is doing the spring, because the spring stretches when we put the object, and this force done by the spring has to be in the opposite direction and has to balance exactly the force of the weight. So what we have here is that in this system, when it's at rest, we have only two forces: the force done by the spring, which is F0, the force of the weight, and both balance exactly, and that's why we have 0 here, because the force of the spring balance exactly the weight. So balance the weight, sorry. So we are writing down here the weight as positive, and why we are doing that? Well, it's a convention. We are using here a coordinate system in the vertical direction. That is our y coordinate. We are putting 0 exactly when the spring is at rest. Positive if it moves downwards is positive. If the spring is moving in the other direction, then we have negative coordinates. So with that convention, positive downwards, the weight is positive and this force is negative. What we said here. Now what happens when the spring is moving? When the spring is moving, when we pull it a little bit and we release, then the spring is going to oscillate back and forth. So we are going to have this situation here. The forces that we had before, the weight is still there and it's not changing, and we are going to call F0 the force that balances the weight exactly. Since the spring is moving, there should be another force which is again done by the spring. What happens is when the spring is stretched more, the force done by the spring is bigger, and we decompose this force into two parts: the force F0 that balances the weight and the rest. So now in this situation, what we have is mass times acceleration is equal, well, these two forces that add up to 0 plus the extra force that we call, let me write it in green, is the force of the spring, the extra force that does the spring. The spring now is doing more force because it's stretched longer than here. So the extra force is that. All this is done by the spring. So we need to know what is the expression for this force, and that force is actually measured in the lab. One can find out that that force Fs of y actually depends on the displacement, on the how far from equilibrium we are, and is proportional to the displacement, with a proportionality constant positive and in the opposite direction of the displacement. So we have a big negative sign there. So when the displacement, like here, for example, the displacement is positive, the force is in the other side, is negative. When the displacement is here, negative, we are compressing the spring, the force is going to be on the other side. That's why always opposite to the displacement. This is called Hooke's law. It was measured in the lab by Robert Hooke around 1660, and the name K is called the spring constant that we wrote over there. So with all that, we can have Newton's law for this system, and it's going to be mass acceleration is equal to negative ky. We can move that term to the other side, and we're going to write it as mass acceleration plus spring constant position equals 0. And you see, this is a second order right here. This is a second order and it's linear differential equation. So this is the main example, the mass spring system, and we are considering the case of no friction. Another important example is, again, a mass spring system, but this time with friction. For example, when we have the mass spring system oscillating inside water. So in that case, we are going to have a picture more or less like this. We have our spring oscillating back and forth inside water. And everything else is the same. We have our coordinate system as before. We have the spring that when it's at rest, there is a force that done by the spring that cancels the weight, and the object and the spring doesn't move. We take the spring out of equilibrium, and then we are going to have the extra force done by the spring, that is the Hooke's law, plus this force. But because we are underwater, now there's going to be a new force showing up, this force here. And this force is actually a force that is due to the friction of the object with the water, and one can measure it, and is in the opposite direction to the velocity. Recall, the Hooke's law is in the opposite direction to the displacement. So if we are stretched, the force is upwards. If we are compressed, the force is downward. That is Hooke's law. But this force is in the opposition to the velocity, so it depends in which direction the spring is moving. So in this case, as before, we have Newton's equation of motion, mass times acceleration equal force, and this force is all the forces acting on the object, which in this case is the weight, and this force that cancels the weight, plus the spring force, the Hooke's law, and now we have a new force. So we have 3 forces now, 4 forces. These 2 cancel out, and 2 more, and these are the 2, Hooke's law and the new force that is proportional to the velocity in the opposite direction. So Hooke's law and the damping force is called due to the friction of the object with the water. So let's recall that yes, what we have here is Hooke's law from before, and now we have a new force that we measure in the laboratory, and this coefficient depends on the interaction between the object and the medium where it's moving. So it's the friction coefficient. And this is a friction force or a damping force due to the water interacting with the object. And now we move these 2 terms to the other side, and what we get is mass times acceleration. Then we have a term proportional to the velocity and a term proportional to the original function. So this is a second order linear differential equation, which is homogeneous because the b term here actually is 0. So these are our 2 main examples of a second order linear differential equation. Let's now go a little bit deeper in the first example we studied before. Let's see that in that example there is something that is called the conservation of the mechanical energy. So what is that? To to understand what is that, before we unveil what is the statement and some remarks, let's do a little calculation. And the calculation we are going to do is we are going to write Newton's equation of motion. So Newton's equation for a mass spring system, mass spring with no friction. Okay, we talk about that. It's not this case, is this case here. So this is the equation. This is the equation, a copy of the mass spring system oscillating without friction. Okay, so the spring has to move in a way that the function y of t is solution of this equation. Okay, so what we are going to do now? Now let's grab this equation again. Now let's make a little bit of space here, and yeah, here more or less. And let's multiply this equation because we want to. Let's multiply this equation by the velocity again, the velocity function. We can always do it, and we can always multiply this 0 by the velocity, which again is going to be 0. We are not going to change anything on the right hand side. Now, just because we want to play with math, let's distribute this product here. What do we get? We get the mass times the velocity times the acceleration plus the spring constant, the position, and the velocity is equal 0, isn't it? Okay, so what? So now let's take a closer look at this product and this product here. And let's recall something that we should know from our previous calculus classes, which is the chain rule for derivatives. Chain rule. For example, suppose you have a function y squared and you compute the derivative. What is that equal to? Well, because of chain rule, that is equal to 2 times y prime. That is chain rule. Okay, great. So notice what we have here. It's exactly what we have here. So there is a way we can rewrite this term. So let's put equal 0 here because this is equal 0. We can rewrite this term as how we can rewrite it. Well, the only thing we need to do is divide this equation by 2. So we divide by 2, 1/2 y squared derivative is y prime. So we can put that here and say this is the same as k over 2 y squared all prime. Is it? All right, now let's change colors, and now let's use chain rule, but now let's use it in here, in y prime square. What is y prime square derivative? Well, the derivative of a function square is 2, the original function, which is y prime, times the derivative of that, y double prime. Notice that what we have here is exactly what we got here. So if we divide by 2 this equation, we have 1/2 y prime square all derivative equal exactly y prime y double prime. Perfect. So that is chain rule. So we can come back here and say this is the same as mass over 2 y prime square derivative of that. So now is a good time to introduce the notation that the velocity, a function of time, is y prime. If we do that, the equation above is a little bit nicer, written as v squared derivative m over 2 plus k over 2 y squared derivative. But because of the properties of the derivative, this constant, we can put it inside the derivative because we can take it out, so we can put it in. And the same here. So we can put all the constants inside the derivatives, and then we have something like this. 1/2 mass velocity squared, recall is a function of time, plus 1/2 k position squared, function of time, derivative is equal 0. So the solutions of the spring, the function y that describes the spring, has to satisfy, because it satisfies Newton's equation of motion, it also satisfies this equation. But this equation says that this quantity here is constant along the motion because it has derivative 0. So this quantity is pretty important. So we are going to give it a name, and we are going to call it energy. And then what we have discovered is, well, if we introduce this quantity E of t, which is mass over 2 v squared plus k over 2 displacement square, if we introduce this quantity, because of Newton's equation of motion, this quantity satisfies that E prime is 0, which means that this quantity, the energy, has to be constant, and if it's constant, is equal to the initial energy. Interesting, isn't it? So we have, by playing around with Newton's equation for a spring, we have discovered that spring has to move in such a way that it always keeps this particular function of velocity and position constant, because the derivative has to be 0. We give a name, mechanical energy, and we can rewrite things in that way. And what we have discovered is the conservation of the mechanical energy, and we should say here for the mass spring, only for this system. And here it is. All solutions of the mass spring system without friction, see, it's important, mass spring system, no friction. Without friction, so this the solution of this equation satisfies that this quantity, where v is the derivative, so velocity, is constant in time. Constant or constant in time. Is constant in time. More names. The first term, the term that is proportional to the velocity, is called kinetic energy. The term that is proportional to the displacement is called potential energy, and the addition of the two is called the mechanical energy. And this is the conservation of the mechanical energy. Why this is interesting? Well, it's very interesting because we discover a quantity that no matter how the spring is moving, it's always constant. So even if we don't know how to solve for the differential equation for the displacement, we can always use this conservation to get information from the system, because this equation is always satisfied with this function. For example, suppose you have this spring with a particular spring constant, a particular mass, and is moving upside down. Find the equation for the spring. Well, that equation, for example, is Newton's equation of motion, so solution. The equation, part 1, the equation is just mass, acceleration, plus the spring constant displacement equals 0. We are giving the spring constant and the mass, so they are saying mass is equal 1 grams, and always check that the units are the same. K is 2 grams over second square, so the same units, so grams and grams. And then the equation is obviously y double prime plus 2y equals 0. That is not difficult at all. What is the energy? Well, the energy, we have said, always is, for this mass spring system without friction, is mass divided by 2, the velocity square plus, which is a function of time, recall, plus the spring constant divided by 2, the displacement square. Okay, mass is equal 1, so in this case the energy is going to be 1/2 the velocity square as function of time, and case 2, so y square. This is the energy in our system, very simple. Recall that the velocity here, I'm calling velocity to y prime. Alright, and now suppose that we have an initial condition for our spring. Initially is at the displacement 1 with velocity 2. Since both are positive, the velocity is downward and the displacement is downward. So let's say that means 3. Our initial condition is y0 equal 1, so downwards is down displacement, and the velocity v0 y prime at 0, which is v0, is 2. Okay, and this is downward also. Okay, what happened with that? Well, find what is the maximum velocity achieved by the spring. Or how do we even find the maximum velocity if we don't know what is y of t? In order to, one possibility to find this answer is to find the solution of the differential equation, then find the derivative, and then maximize this function, find the time where this function is the maximum. But we don't know how to find y of t. But we do have the conservation of the energy. So what is this equation? This equation says that the energy at any time has to be equal the energy at the initial time. What is the say? We have the formula for the energy: 1/2 the velocity square at any time plus the position square at any time has to be equal the initial energy, which is 1/2 the velocity at 0 square plus the position square at 0. But we have these values right here, 1 and 2. 2 here, 1 squared. So we know that this is 1/2, and then is 2 squared plus 1 squared. So we have 4. So 4 divided by 2 is 2 plus 1. So this is 3. So essentially, we know that the spring has to move in such a way that 1/2 the velocity square at any time plus the position square at any time has always, in this particular example, has always add up to 3. This is the conservation of the mechanical energy. And now when this the velocity is going to be maximum, v is going to be maximum when, notice that we have a square. So this can never be negative, but it can be 0. V is maximum when y at t1 some time is 0. So then we have the equation 1/2 v maximum squared plus 0 has to be 3. So obviously v maximum has to be 2, so 6 square root, positive or negative. I'm going to choose the positive, it doesn't matter. Positive or negative, it says in which direction. Okay, that is the maximum velocity. This is up. And Now we can also do another calculation that is not required in this example, but we can also find what is the y maximum. Or let's put it like this. Y maximum. The maximum displacement is going to be when the other term is 0, so when the velocity at the particular time is 0. Isn't it? Because this term is going to be maximum when this is the lowest possible, and because of the square, the lowest possible is when it's 0. So we have 0 plus, in this case, y maximum squared still equal 3. So the y maximum, the maximum displacement has to happen at plus or minus square root of 3. So this is how we can use the mechanical energy to solve some problems. Notice that these problems have physical meaning, so this is reasonable that the maximum velocity is going to be when the displacement is 0. When the displacement is 0, when the spring is moving through equilibrium. At that point, the spring is having the maximum velocity upwards or downwards. But if when is passing through the rest position, which is y equals 0. And y maximum is when the velocity is 0, that is, the maximum elongation is when the spring is going down and then is changing to going up. At that changing point, the velocity is 0. So there is the maximum displacement, y maximum. Everything perfectly reasonable with our intuition. And now we can find the actual numbers by using the conservation of the mechanical energy. What happens with the conservation of the mechanical energy when we have friction? Well, with friction, the mechanical energy is not conserved anymore because of the friction. And what happens in that case, after much more study, is that people discover that the mechanical energy is actually getting transformed into a different type of energy that it has to be defined and quantified, and it's called thermal energy, heat, what we usually call heat. So if we don't account for the heat and we only look at the mechanical energy, then the mechanical energy is not going to be conserved. What is going to be conserved is both, but we are not going to, in our class, we are not going to describe the thermal energy, so all we can say is that the mechanical energy, it goes down. And this is the statement here. Suppose we have a mass spring system, but now with friction. So we have this term now. So then we define the mechanical energies as before with that part of the equation. And we discover that the mechanical energy, then the derivative is not 0 as before, but is always negative. Or 0, depending on the velocity. If the object is moving, then it's going to be negative. And the proof is very simple. It's just repeat the calculation we did before, but now we have a new term that we need to keep in our calculations. So we have mass, acceleration, plus the damping coefficient velocity, plus the spring constant displacement equals 0. And as before, we multiply the whole equation, both sides, by the derivative of the positions of the velocity. So we are going to now distribute in 3 terms over here. So we end up with mass, then the first derivative and the second derivative, then and now notice the first derivative square, and then k, the function, and the derivative equals 0. So let's introduce now the velocity as y prime, and then all this can be written by the chain rule as we did before, 1/2 mass velocity square prime. This is the new term, we keep it as it is, v, the damping coefficient v square, we don't do anything here. And here we use chain rule again, so we have there it is, 1/2 k, And now we have, y squared prime equals 0. So as before, we can put this term and this term together, and we move this term to the other side. And if we do all that, we are going to have that the derivative of 1/2 mass velocity square plus 1/2 k position square, the derivative of all that is actually negative or 0, is the v square, which is less or equal 0. So what we obtain, as before, this is the mechanical energy that we have introduced before. And now the equation says that the mechanical energy is negative, a coefficient that is negative, v square. So what that says is that E of t, the mechanical energy, is not an increasing function, is constant or is decreasing, so not increasing. And most of the time, when it's not constant, is decreasing. So we are losing mechanical energy when we have friction. That is the statement that we have discovered here. We have one more example before we finish our video today, and that example is the following. Suppose we have a heavy object falling near the Earth's surface. For example, you drop a pencil from your desk. So what do we mean by heavy? Heavy, we mean heavy enough so the friction with the air is not important. So we are going to, in this case, in this example, we are going to discard any friction effects. So suppose then we have an object falling on the surface of the Earth, no friction here because the object is heavy enough, and suppose we have some initial conditions. Initial velocity 0, for example, when the pen starts falling from the desk, and initial position 10 meters from the ground. It's a very tall desk. Find the velocity v1, which is the velocity when the object touches the ground. How we can do that? Well, we need to do some adaptation of the ideas we mentioned before about the conservation of the energy. So this is our system. We have the ground, we have an object, we have an initial position that maybe is a good idea to write it down. Suppose this is our initial position that we call it y at 0, that the 10 meters, and the initial velocity is going to be 0, and the object is falling, and is falling because the weight is always acting, the acceleration of gravity is always acting on the mass of the object, and we have the weight force acting on the object. And notice now that the force is negative because we switch our coordinate system, and for this type of examples that we are going to put 0 at the ground, but vertical coordinate as usual is positive upwards. So because we are not hanging things, so then positive is upwards, and because of that, because the weight is always pointing towards the ground, and now pointing toward the ground is going to be negative. So what is Newton's equation of motion in this case? In this case, we have mass acceleration equal all the forces, and there is only one force, the force of the weight, that is negative g, and recall the negative is because now positive is upwards. So how we are going to find the velocity of the object touches the ground if we don't know how to integrate this function? Well, actually we know how to integrate. This is a constant, this is a constant, we integrate twice and we could do it. But we can also do it with the mechanical energy. Because we don't have friction, this equation should have a mechanical energy that is conserved. It's going to be a different formula from the spring mechanical energy, but there is a mechanical energy conserved in this problem. So what we are going to do is we are going to find the mechanical energy in this system. Mechanical energy. how do we going to find the mechanical energy? Well, let's rewrite the equation like we had before. Mass second derivative plus mass acceleration of gravity is 0. What did we do before to find the mechanical energy? We multiply the equation by a function that transforms the equation after the multiplication into a total derivative. And that function we use was the velocity. Alright, we can still do that. And now what we are going to have is, let's go over here. What we are going to have is mass, velocity, acceleration. This is exactly what we had before, plus mass, acceleration of gravity, velocity equals 0. Now the chain rule says that this is going to be equal to mass over 2 v prime square all that prime. Recall this is the calculation we did with the chain rule in the spring. It's kind of getting tight here. Okay. And over here, what do? Nothing. We leave it as it is because this is already a total derivative. So let's introduce v to be y prime, and then we have mass over 2 v square derivative plus, and here we have constant v prime equals 0. So this obviously is something of the form 1/2 mass velocity square plus mass acceleration of gravity position. Recall this is a function of time, this is a function of time, all that derivative equals 0. So now we have a conserved quantity here because the derivative is 0. So now we are going to define this to be our mechanical energy, because with that definition E prime of t is 0, and therefore the energy is conserved, equal the initial energy. But now our energy is different from the spring because, well, different forces. So we still have the kinetic term, the v squared term, but now we have a linear term in the position. So now we can know what is the velocity when it hits the ground. Very easy, because what we know is that the initial energy, so the energy at any time, here is any time square, plus the mass times acceleration of gravity and the position at any time, has to be equal the initial energy, which is mass, the initial velocity, and on here we put the initial position. But the initial condition says that this is 0 and this is 10, isn't it? These are the initial conditions. So we have the initial energy, and the initial energy is mass, acceleration of gravity, initial position. So when it's going to reach the ground? So this is always constant, and we have 1/2 mass velocity squared, a function of time, mass acceleration of gravity, position at any time has to be constant, equal that. Now when it's going to reach the ground? So it reaches the ground, at the ground, that means T1 such that obviously y at T1 is 0. We are at the ground. So the equation we have for V1 is 1/2 the mass, the velocity squared at the ground plus 0 has to be the mass, acceleration of gravity, initial position. So we cancel now the mass, we multiply by 2, and we compute the square root, and the quantity we are looking is plus or minus, and now we need the plus or minus because it's going to be minus the solution because it's going down, the square root of 2 acceleration of gravity, the initial position. And we are going to choose the negative solution because this is the correct sign for the velocity. So that's it. We put the numbers. We are going to use, we are going to approximate g to be 10 meters over second square, just to don't use calculator. And then we have that is minus the square root of 2 times 10 approximately, let's say approximately, and then the initial position was also 10. So we have a 10 squared. So we end up with the v of at it reaches 0 approximately at negative square root of 2 times 10. And now that we are approximating, square root of 2 is approximately 1.414 and something else. So v of T1 is approximately 14.14 meters over second. So that is how we can get the velocity at the ground by using the conservation of the energy in this system where we have a particle falling near the surface of the Earth. And this is a good place to stop. See you guys in the next video.